So now we see the first experiment, Reynolds experiment, where the setup is drawn like that. You are supposed to draw the setup in the examination. You will have a collection tank, you have some tank, you have a pump, you have a glass pipe through which the water flows, and let me call this as V1, let me call it as V2, and here this is a KN40 tank, and this will come here. Okay. Now what we do is first step, and now remember all the steps what I am explaining you are supposed to write in the examination. Point number 1, ensure that water is there in the storage tank, okay, or else you fill it. So up to here it will be there. Now once the water is full, what you should do, you should start this pump. When you start the pump, what will happen? Water from here it goes and then falls into the collection tank through the valve V2. So you should open valve V2 also. Then of course the water will fall into this collection tank, and the collection tank is having a provision of overflow. So once the tank is filled up to a particular level, through the overflow the water falls into the storage tank. So even if the pump is on, nothing will happen, no damage will be there, because water from here it goes and then falls again into this tank. Energy will be wasted, but the pump is, the entire system is, there are no overflows are there. That is the important design of this system. Next, how to perform this experiment is, you know very well that the main purpose of performing the Reynolds experiment is to visually predict whether the flow is a laminar flow, transition flow, or turbulent flow. So as I said, in the here you have a glass pipeline in which water is flowing, and then this is the line. If you are able to see this line, that is the dye line, okay. So then we say, if you are going to see a straight line, then we say this is a laminar flow. So when the Reynolds number is up to 2100, we can say it is a laminar flow. Now when you increase the flow rate, what will happen? Slowly the figure number 1 becomes figure number 2. So how the line will have a wave patterns, and these wave patterns indicate that the flow is shifting from the laminar to transition. So in between Reynolds number 2100 to 4000, we see this, and once you see that the filament is vanished, as in this diagram number 3, if you see here, the figure number 3, there is only water is present here. We are not able to see any dye color, any line you are going to see. That indicates that the total mixing is taking place, and it is in a turbulent region where the Reynolds number is greater than 4000. So by seeing these flows only, we can say whether the flow is a laminar flow, transition flow, turbulent flow. That is the reason why we are going to perform this experiment. Please remember this very well. Why should we perform this experiment? We perform this experiment only to visually predict whether the flow is laminar, transition, or turbulent. So what we do in our lab is, first we will open this valve very slowly so that the drops of water falls into this. And as you know very well, once you open the valve, what will happen? The level of the water inside the collection tank decreases. So generally you start at a particular point, and then what you do? You open the valve. So once you open the valve, what will happen? The level of the water will be coming down, and then for example, if it is decreasing by 1 centimeter, then you say stop and then note down the time, and again you give one more disturbance to it, open this valve. So again after the next reading, then again you catch it for 1 more centimeter. So like that we perform the experiment. Then we have a set of readings, then we have a tabular column. From there we start our calculations. So here, what is the operating procedure for doing this experiment is very important, which you are supposed to write in the examination. As I said, first step, the water in the storage tank should be there, it should be full, and then once this tank is full, what will happen? You start the pump, and then you open this valve V2, then the water will fall into this tank, and from the overflow it comes down. So you can switch off the pump. So now the experiment setup is ready for the operations, and remember V1 was closed till now. So once the water level is full in this tank, and then what you do, already this is open, and then we give connection to it at the center. This will go as it is, no problem. So when you open the valve slowly, what will happen? From this collection tank, the water will be flowing through this glass pipeline, and then it is falling into this storage tank. And as I said that for every 1 centimeter you will be taking the reading. As 1 centimeter drop, you will be taking the reading, and then you will be opening the valve consecutively to find 6 or 7 readings. So this is what you are supposed to write in the examination. So you should write in the examination aim of the experiment. Okay, you should write the aim of the experiment. You should write this diagram also, and then you should write the operating procedure, and then you can start the calculations. Okay. So now with this, so what you are going to calculate here? So you will have initial reading in the collection tank, final reading in the collection tank, the time of drop. Okay, like that you will have a number of readings. So with this database, we will go for the calculations. So after performing the experiment, this is the tabular column which you are supposed to draw in the examination. In the first column, you will have initial height of water in the collection tank. Then you say start, and then you have a stopwatch. For 1 centimeter drop, you will note down what is the time, and then finally report here final height of the water in the collection tank. So this you can have it in meters directly. Now time of collection in seconds, how it is dropping from top to bottom, how much time it has taken, seconds. Then in the previous video I have shown you how to calculate the volumetric flow rate. So here you will write the values of volumetric flow rate in meter cube per second. Then you have average velocity, then you have the Reynolds number formula. So with this we finish off our tabular column. Now let us calculate how to calculate the average velocity. You know very well that for example initial height is equal to, I will make one point A and final is B, time of collection is equal to T. Okay. So you know the formula. So if you know this, yeah, for your sake. So final height is Q is equal to final height, that is B, minus initial height is A, divided by the time of collection into, see the top view of that collection tank, and then note down its cross section area. I have shown you A into B. So that cross section area will be added here. So with this you get the value in meter cube per second, B is in meters, A is in meters, T is in seconds, cross section area converted in meter, you get in meter cube per second. And then we will give you the diameter of the glass pipeline. Okay, internal diameter of the glass pipeline we will give you, and that is given by D. So with this D, you will convert it to cross section area. You will find the cross section area, find pi by 4 d square. Now you know velocity I am supposed to find, V bar is equal to Q divided by the cross section area. So Q you get it from here, and then cross section area you got it from this formula, and thus you are going to get V bar. So unit of V bar is meter per second. Next one is the formula for NRE. NRE is equal to rho V bar D by mu. As said in the previous videos, how to calculate the Reynolds number, I gave you this. With this you calculate the value of Reynolds number. Now what you are going to do is you are going to plot a graph. You will have the Q on x-axis and V bar on y-axis. Okay. So this is very important. So you may get some graph, and then first you will be calculating the sorry, here you have so here you have NRE and here you have Q. So you will be completing the values of Reynolds numbers here, okay, all the values, and then you will be having all the values of Q here. So Reynolds number will be there on, Reynolds number will be there on the x-axis, and then Q will be there on the y-axis. So now you get some graph. So now what you do is, first step is what you are supposed to find, lower critical velocity. Meter per second. So how to find this? So mark a point on 2100, and then for example you get a graph like this. Draw a line cutting this point at this one, and you know this Q. This say I will call it as Q1. So Q1 divided by the cross section area. Cross section area is again the same formula, pi by 4 d square. So you get low critical velocity. Similarly at 4000 I will find again one more, this is Q2, then I have higher critical velocity meter per second. This is equal to Q2, this value Q2, the same cross section area, you get an answer. So in this result you will be writing, in the result you will write lower critical velocity meter per second, higher critical velocity meter per second, and this graph is very important. And I repeat once again, what is the significance of Reynolds number experiment? It is used only for pictorially predicting how the flow is there, whether it is a laminar flow, transition flow, turbulent flow.